In previous videos, we saw why and how quantum particles can be described as excitations in a field. In the very early days of quantum mechanics, it was recognized that electromagnetic wave fields, so light, can be described as a collection of particles called photons. Then by the wave-particle duality, if electromagnetic fields can be described as a system of many photons, then a system of many particles, such as electrons, can be described as some sort of an electron field. Quantum field theory was developed by Pauli and Weisskopf as an alternative theory to Dirac's theory of holes. Dirac had discovered a relativistic quantum wave equation that successfully describes the fine structure of hydrogen, but it also predicted the existence of negative energy levels. Dirac proposed that an infinite sea of electrons occupied these negative energy levels, and holes in the sea would be observed as antiparticles. The anti-Dirac quantum field theory of Pauli and Weisskopf made the same prediction of antiparticles, but it avoids the awkward physical interpretation of holes in an infinite sea of electrons. Quantum field theory also predicts that even in the lowest energy state, so the vacuum state, the field has random fluctuations due to Heisenberg's uncertainty principle. In this video, we will look at some very important experimental evidence that these vacuum fluctuations are indeed real, and have an observable impact on the energy levels of hydrogen. In particular, we look at a specific shift of an energy level, which is known as the Lamb shift, which was experimentally discovered by Willis Lamb in 1947. His discovery was in part thanks to his experience with radar technology during the Second World War. To understand what this Lamb shift exactly entails, we recall the expression for the hydrogen energy levels that follow from the Dirac equation. These energy levels depend only on the total angular momentum number, not on the separate contributions of the orbital and spin angular momentum. Therefore, if we consider a state with orbital angular momentum 0 and spin angular momentum 1/2, we would expect the same energy as for the state with orbital angular momentum 1 and spin angular momentum -1/2. Because these two configurations yield the same total angular momentum of 1/2. So the Dirac theory predicts that the 2s1/2 state of hydrogen, with orbital angular momentum 0, has the same energy as the 2p1/2 state, with orbital angular momentum 1. However, what is observed experimentally is that these two states have slightly different energies. This energy difference is called the Lamb shift, and we will see that it can be explained by the interaction of the electron with the vacuum field fluctuations of the electromagnetic field. Therefore, the Lamb shift provides very important experimental evidence for quantum field theory. An intuitive interpretation of this phenomenon was given by Theodore Wilton shortly after Willis Lamb measured the Lamb shift and Hans Bethe gave the first theoretical calculation of this effect. In this interpretation, we consider the shapes of the orbitals of the two states. The vacuum field fluctuations randomly bump the electron around, so the orbitals are slightly blurred. Therefore, the electron sees slightly different parts of the electrostatic potential of the atom's nucleus, and this shifts the energy of the state. When this energy shift is calculated, it turns out that it depends on the Laplacian of the Coulomb potential, which is non-zero only at the nucleus. For the p state, the orbital doesn't go through the nucleus, so the energy of the state is not shifted by the vacuum fluctuations. The orbital of the s state, however, does go through the nucleus, so its energy is shifted. Therefore, the two states which have the same energy in the Dirac theory will have different energies due to the interaction with the vacuum field fluctuations, and this difference in energy is measured as the Lamb shift. To calculate this Lamb shift theoretically, we will use perturbation theory. The electromagnetic field will be considered as a perturbation to the electron state. When we discuss second-order perturbation theory, we will find that the resulting shift in energy can be interpreted as the consequence of the sum of all possible virtual transitions. That is, the perturbation may excite the electron to a different energy state. Then, the electron returns to its original energy state. This transition gives a certain contribution to the second-order energy perturbation, and all the other virtual transitions to different states also each give their own contribution. Energy is in general not conserved during these virtual transitions, and they are not physically observable. Therefore, it is good to have this mental picture to keep track more easily of calculations in second-order perturbation theory, but it probably should not be taken too seriously as an accurate picture of physical reality. When we calculate these perturbations to the electron energy, we find corrections that are infinite, because we sum over infinitely many modes, or frequencies, of the electromagnetic field. We will see that the interaction of the electron with its own electromagnetic field can be interpreted as a contribution to its mass. So correcting for this infinite quantity is called mass renormalization. Furthermore, we will see that in the calculation of energy perturbations, it matters significantly whether we take into account the existence of positrons or not. The reason why this matters is because if we allow for the existence of positrons, extra virtual transitions are possible which contribute to the energy perturbation. For example, as the electromagnetic field interacts with the electron field, a virtual positron-electron pair can be created. Then, a positron and electron can annihilate to return to the original state with just one electron. So let's start with a recap of perturbation theory. We start with the Hamiltonian of an unperturbed system, whose eigenvalues, or energies, and eigenstates are known. Then we add a perturbation to the Hamiltonian. We want to find how this perturbation affects the eigenvalues and the eigenstates. To keep track of the different orders of the corrections to the states and energies, we expand them in terms of the perturbation strength epsilon. We can find the different orders of the corrections by collecting all the terms with the same power of epsilon. For example, in the zeroth order approximation, we collect the terms that do not depend on epsilon, and we find that the perturbed system is approximately the same as the unperturbed system for sufficiently small perturbation strengths. The first order correction is found by collecting all the terms that are linear in epsilon. To find from this equation the first order correction to the energy, we take on both sides the inner product with the unperturbed energy state. We see that two terms cancel out, because the unperturbed energy state is an eigenstate of the Hamiltonian, whose eigenvalue is the unperturbed energy. Since the inner product of the unperturbed eigenstate with itself equals 1, we find that the first order correction to the energies is given by the diagonal elements of the perturbing Hamiltonian, if it is expressed as a matrix in the eigenbasis of the unperturbed Hamiltonian. To find the second order correction, we collect all the terms that are quadratic in epsilon. We again take on both sides the inner product with the unperturbed eigenstate. We cancel out the terms that are equal thanks to the eigenvalue equation of the unperturbed system, and we recognize that the inner product of the unperturbed eigenstate with itself equals 1. The resulting equation depends on the first order correction to the energy eigenstate, which we haven't yet calculated. So let's calculate it now. Let's revisit the equation for the first order correction, where we collected all the terms that are linear in epsilon. We collect the terms with the first order correction to the eigenstate. we write this first-order correction as a linear combination of eigenstates of the unperturbed system. Note that the eigenstate to which we are finding the perturbation is not included in the linear combination. This is because that term would not affect the left-hand side of the equation. We plug in this linear combination in the equation, and we substitute the unperturbed Hamiltonian with the unperturbed energy levels. When we take on both sides the inner product with one of the unperturbed energy eigenstates, we select one term of the linear combination, because the eigenstates are orthogonal. For the same reason, the term on the right-hand side vanishes. We can now solve for the weights of the linear combination, which gives us an expression for the first-order correction to the energy eigenstate. We have now found the expressions for the first-order and second-order perturbation to the energy levels. The first-order corrections are given by the diagonal elements of the perturbing Hamiltonian. Loosely speaking, one can think of this as how the perturbation directly shifts the energy levels of the system. The second-order corrections, on the other hand, involve the off-diagonal elements of the perturbing Hamiltonian. These can be associated with the energy due to transitions between different states. That is, we start with an unperturbed eigenstate. Then we transition to some other unperturbed eigenstate. And from there, we return back to the original state. To find the total second-order correction to the energy, we need to sum over all states to which we can transition. These transitions don't occur physically, but they are merely an intuitive interpretation that we assign to the formula we found. Therefore, we call these transitions virtual transitions. We see that the energy contribution of each virtual transition is divided by the energy difference of the initial and final state. That is, if the virtual transition conserves energy better, it contributes more to the total second-order energy correction. Also note that the sign can be either positive or negative. This means that the energy contributions of different virtual transitions can partially cancel each other out. We found the first-order correction to an energy eigenstate if the system is perturbed by a time-independent perturbation. However, when we consider the interaction of an electron with the electromagnetic field, the perturbations will be harmonically oscillating in time. In the following, we will see why and how we can still use the results of time-independent perturbation theory in this case. In the time-independent perturbation theory, we started with the time-independent Schrödinger equation. This is an eigenvalue equation where the eigenstates do not change in time. In time-dependent perturbation theory, we will consider states that evolve in time, so we will denote the time-independent states with a tilde to make the distinction between time-dependent and time-independent states clear. We can now write the time-dependent Schrödinger equation in terms of time-dependent states, and the Hamiltonian is perturbed by a harmonically oscillating perturbation. We expand the product on the left-hand side of the equation. Since we consider only the first-order correction, we neglect the term that is quadratic in the perturbation strength. Moreover, we can cancel the terms that satisfy the unperturbed Schrödinger equation. Similar to what we did previously, we write the first-order correction to the energy eigenstate as a linear combination of the unperturbed energy eigenstates. Note that we can write the unperturbed time-dependent states as the time-independent states multiplied by a time-dependent complex exponential. When we plug this linear combination into the equation, applying the Hamiltonian to the time-independent eigenstates yields the energy eigenvalues. The time derivative can be calculated with the product rule. The time-dependent unperturbed eigenstate is written in terms of the time-independent eigenstate. One term appears on both sides of the equation, so they can be cancelled. By taking the inner product with an unperturbed time-independent eigenstate on both sides, we select one term of the summation. To solve for the coefficient for that eigenstate, we integrate with respect to time. We plug these coefficients into the expression for the first-order correction to the energy eigenstate to find our final result. We can now compare this result for a harmonically oscillating perturbation to the result for a time-independent perturbation. For a clear comparison, we write the time-independent eigenstates in terms of the time-dependent eigenstates. Then we can see that the results for the time-independent and time-dependent cases are the same if the energy of the intermediate state of the virtual transition includes the photon energy. This accounts for both the time-dependent complex exponential and the term in the denominator. Therefore, we can use the results of time-independent perturbation theory when we calculate the interaction with the electromagnetic field, as long as photon energies are included in the energies of the intermediate states of virtual transitions. We will now see how vacuum fluctuations affect the electron energy in the non-relativistic approximation. In a previous video, we saw how Dirac used the non-relativistic interaction between the electron and the electromagnetic field to explain photon absorption, emission, and scattering in quantum theory. The interaction can be split in a term that is linear with the vector potential and one that is quadratic with the vector potential. Note how this is different compared to the relativistic case. If we calculate the interaction term for the Dirac equation, we find that there is only a linear term. Furthermore, we saw how the electromagnetic vector potential can be quantized by using creation and annihilation operators. With these results, let's look at the first-order corrections to the energy. These are given by the diagonal elements of the perturbing Hamiltonian. That is, when we apply the perturbing Hamiltonian to the unperturbed initial state, the resulting state should not be orthogonal to the initial state if the energy correction is to be non-zero. The state of the electromagnetic field can be expressed in terms of Fock states, where we specify for each mode how many photons occupy it. When we apply the vector potential operator to a state, then the annihilation and creation operators lower and raise the photon number for a certain mode. Therefore, the output state is orthogonal to the input state, and the first-order energy correction is zero. However, when we consider the interaction term that is quadratic in the vector potential, we have products of creation and annihilation operators. Such products yield the number operator, and if we apply the number operator to a Fock state, the resulting state is proportional to the input state. Therefore, the first-order energy correction will be non-zero for this interaction term. However, this energy correction diverges quadratically because we have to integrate over all field modes, which have different wavelengths and directions. This is not a desirable result, but because the same correction applies to all electrons equally, one can argue that this infinite energy correction is irrelevant, because for physical processes, it's only the energy differences that matter. So to see how the linear interaction terms contribute to the energy correction, we turn to the second-order perturbation. We saw that here, the virtual transitions between states contribute to the energy correction, and that's exactly what the creation and annihilation operators do. They describe transitions between different photon states. The initial state consists of an electron that has some momentum p, and there are no photons. This means that we will investigate the interaction between the electron and the vacuum fluctuations. The intermediate states in the virtual transitions are described by an electron with some different momentum q, and a photon with some momentum h bar times k and polarization state j. We will see in a minute that the photon momentum and electron momentum are related in such a way that total momentum is conserved. The energy of the intermediate state is given by the kinetic energy of the electron plus the energy of the photon. Note that no photons can be annihilated if the electromagnetic field is in the vacuum state. So the interaction Hamiltonian only involves the term with the creation operator. So to calculate the matrix elements of the interaction Hamiltonian, we plug in the relevant term from the vector potential, the initial state, and the intermediate state. When we calculate the integral over space, we find that the exponentials reduce to a delta function. This delta function enforces conservation of momentum. With these results, we can calculate the second-order correction to the electron energy due to interaction with the vacuum fluctuations. We can consider two different limits. In the non-relativistic limit, the electron momentum is small, and the electron kinetic energy can be approximated with the squared momentum. The photon energy is way too small to create an electron-positron pair. If the momentum is very large, then the electron energy scales linearly with momentum instead of quadratically. Let's first investigate the energy correction in the non-relativistic limit. The squared modulus of the matrix element is found to be proportional to the squared electron momentum divided by the photon momentum. The energy difference between the initial and intermediate state consists of the initial kinetic energy of the electron, the kinetic energy of the electron in the intermediate state, and the energy of the photon that is generated in the intermediate state. By using the conservation of momentum, we can eliminate the kinetic energy of the electron in the intermediate state. For small photon momenta k, this expression scales linearly with k. For large photon momenta, the expression scales with k squared. However, for large photon momenta, the non-relativistic approximation breaks down, so the electron energy doesn't scale with the squared momentum anymore, so this scenario is not relevant. To find the second-order energy correction, we must sum over all intermediate states. This means that we have to integrate over all photon momenta. If we combine these results, we find that the energy correction scales linearly with the upper bound for the photon momentum. Note, however, that due to the non-relativistic approximation, the photon momentum cannot be arbitrarily high. To cover the regime of high photon momenta, we consider the relativistic expression for the electron energy. From this, it also follows that the energy difference between the initial and intermediate states scale linearly with photon momentum, so the second-order energy correction still scales linearly with the upper bound for the photon momentum. Therefore, we conclude that when the electron interacts with the vacuum fluctuations, the energy diverges linearly. So the total energy is given by the classical expression for the kinetic energy, plus some divergent rest energy, plus some divergent energy that scales with the squared electron momentum. To avoid this problem of linear divergence, one can think of absorbing it into a finite effective mass that is measured experimentally. That is, we can postulate that a bare electron has some infinite bare mass and that its interaction with the electromagnetic field introduces an infinite electromagnetic mass. These two masses can never be observed separately, because one cannot switch off the interaction of an electron with the electric field. The two infinities cancel each other to give a finite measurable mass. This idea is called mass renormalization. The problem of divergent interaction energies was noted by Dirac when he developed the quantum theory of dispersion using the non-relativistic approximation. After the relativistic Dirac equation was discovered, Oppenheimer found that this problem still persisted, and that it gave no better results than the non-relativistic theory. However, this was before Dirac had proposed the theory of positrons, or holes in the Dirac sea. This is relevant because in the positron theory there are extra intermediate states where electron-positron pairs are created, which affects the second-order energy correction. Oppenheimer further remarks that this problem is not unique to quantum mechanics, but it was already known from classical theory. Dirac later explained that the reason why this issue had not been resolved sooner was because the development of quantum mechanics already showed that the classical theory was inadequate. So there was little interest in trying to interpret anomalies in a theory that was already known to be incomplete. One might have hoped that quantum theory would reveal an elegant resolution to the problem, but that unfortunately didn't turn out to be the case. So let's see what was already known about the electron self-energy from classical theory. Hendrik Lorentz published already in 1909 some by then old ideas on the structure of the electron. He recognized that it is very bold to theorize on the internal structure of a particle that is so extremely small. However, he argued that such speculations are nonetheless necessary to make the equations of the theory and their interpretation consistent. These considerations led to an interesting hypothesis, namely that all mass is electromagnetic in origin. The reasoning behind this hypothesis is the following. We can define mass as the thing that relates a particle's velocity to its momentum. If we consider an electron with some radius r, then it has some electric field E. If the electron starts moving with some velocity v, then a magnetic field B is generated. If there is both an electric field and magnetic field, then we can calculate the momentum density of the electromagnetic field via the Poynting factor. The total momentum can be found by integrating the momentum density over space. When this calculation is performed, one finds a relation between the momentum and the velocity of the electron. For small velocities, the momentum is directly proportional to the velocity. From this, one can infer the effective mass of the electron. Note that the mass depends on the radius of the electron. Therefore, if we trust this formula, and we measure experimentally the mass of the electron, then we can calculate the radius of the electron. Furthermore, we see that if the radius goes to 0, then the electron mass diverges. More precisely, we can define a maximum spatial frequency of the electromagnetic field that can interact with the electron. This maximum spatial frequency depends on the size of the electron. We then see that the mass diverges linearly with the maximum spatial frequency. This is consistent with what we found in the quantum mechanical calculation. If the velocity of the electron approaches the speed of light, then the formula for momentum gets an extra factor that is also encountered in Einstein's special relativity. Keep in mind, however, that this result is purely due to classical electrodynamics, without any assumption of Einstein's special relativity. Another thing we can calculate is the energy in the electric field of a stationary electron. The electric field has a certain energy density, which we can integrate over all space to find the total energy. Note that also this energy diverges if the electron radius goes to 0. If we compare the expression for the energy to the expression for the mass, we find a mass-energy relation that is very similar to the one from Einstein's special relativity. The key result here is that the electron must have a finite size if we want to avoid certain quantities becoming infinite. Another argument for why the electron size must be finite has to do with the Abraham-Lorentz force. We know from classical electrodynamics that if an electron is accelerating, it emits radiation. This radiation carries away energy, so the electron must lose energy. If the electron loses energy due to radiation, it means that the radiation must exert some force on the electron. This is called radiation reaction, and it is observed experimentally in, for example, radio antennas. If we know how this self-force is related to the acceleration, then it can be incorporated in the effective mass of the electron. So from energy conservation, we infer that a force must act on the electron. But what is the physical mechanism behind that force? The idea is that different parts of the electron exert forces on each other. Consider, for example, the case where the electron is at some position, and a short time later it is at some other position. At the initial position, different parts of the electron were emitting electric fields, whose interaction travels at the speed of light, which is finite. Therefore, when the electron is at its second position, the forces from the different parts of the electron at its initial location don't cancel out, and the electron experiences a net force. A detailed calculation of this effect shows that one term of the force is directly proportional to the electron's acceleration, so it can be absorbed in the electron's effective mass. Once again, we see that this mass diverges if the electron size goes to 0, so one might infer that the electron should have a finite size to avoid this problem. So for some time, it was believed that the electron should have a finite size. But this view was later abandoned. One attractive idea of this theory was that all mass would be of electromagnetic origin, so the existence of all mass would be explained. This idea was formed at a time where the only known subatomic particles were electrons and protons, which were both charged particles, so the idea made some sense. But when the neutron was discovered, a particle with mass but no electric charge, the theory becomes more difficult to defend. So instead, it became accepted that the electron is a point particle with no finite size. This brings the problem of infinite energies and masses, and they have to be dealt with via some method of renormalization. We now return to the quantum mechanical treatment of the electron. We saw how the non-relativistic treatment led to a linearly divergent interaction energy, and the relativistic treatment without positrons led to a similar result. Victor Weisskopf calculated the self-energy of the electron using the full relativistic Dirac theory that includes positrons. As we will see later, he found that the electron self-energy is still divergent in this theory, but only logarithmically instead of linearly. To understand Weisskopf's calculation, which was different from the usual perturbation method, we will go through the following steps. First, we must turn the Dirac equation into a field theory. This requires that we have a Lagrangian for the Dirac equation, which according to relativity must be Lorentz invariant. To find such a Lagrangian, we must learn how Dirac spinors transform under Lorentz transformations. With that Lagrangian, we can find the conserved Noether charge and current. This tells us how the charge and current are distributed for an electron according to the Dirac theory. With the standard Maxwell theory of electromagnetism, we can calculate the electric and magnetic fields that are generated by the charge and current distributions of the electron. We can then calculate the interaction energy of these fields with the electron charge and current distributions to find the self-energy of the electron. To do this, we use the theory of second quantization, which requires us to find the plane wave solutions of the Dirac equation. So let's start with finding how a Dirac spinor transforms under a Lorentz transform. According to Dirac's theory, the state of an electron is described by a four-component vector called a spinor. This spinor satisfies the Dirac equation, which is here written in its time-independent form, with some potential V. We will now consider the time-dependent equation for a free electron, so the potential is zero. Recall that the momentum operators are spatial derivatives, and the 4x4 Dirac matrices can be written by using the 2x2 Pauli matrices. We will now rewrite the equation in its so-called covariant form, where its Lorentz invariance can be seen more clearly. First we multiply the bottom two equations by -1. Then we move all the terms to one side and divide by the speed of light c. We can now define the four gamma matrices and write the Dirac equation more compactly by using Einstein notation. We will now see how the Dirac spinor transforms between reference frames. We write down the Dirac equation for one reference frame, and we require that the same equation holds for another reference frame, where we denote the coordinates and the spinor with primes. The relation between the primed and unprimed coordinates follows from the Lorentz transform. We assume here the primed reference frame is boosted in the z direction. We can write the primed time derivative in terms of the unprimed derivatives by using the chain rule, and plugging in the expressions that followed from the Lorentz transform. The z derivative in the primed coordinate system can in the same way be expressed in terms of derivatives in the unprimed coordinate system. The x and y derivatives are the same for the primed and unprimed coordinates. We can now write the Dirac equation in the primed coordinate system in terms of derivatives with respect to the unprimed coordinates. In this equation, only the spinor remains primed. We can collect the terms containing a time derivative, and we collect the terms containing a z derivative. We now have two equations with only unprimed coordinates, and both equations must be valid. Using this constraint, we will find the relation between the primed and unprimed spinor. That is, we will find how the spinor transforms under a Lorentz transformation. To do this, we will write out the four equations for the four components of the spinor. For example, using the definitions of the Pauli matrices, we can write out the equation for the first component, and in the same way we can write down the other three components. We also write down separately the four equations for the components of the unprimed spinor. When we put these sets of equations side by side, we can make an educated guess for how the primed spinor components are related to the unprimed spinor components. With this assumption, we only need to find the expression for the coefficients a and b. We can do this by plugging this assumed relation into, for example, the first unprimed equation. We can compare this result to what we get if we multiply the first primed equation by a and add it to the third primed equation multiplied by b. This way, the right-hand sides of the equations match. We arrange the terms so that they can be easily compared to the terms in the unprimed equation. By comparing the terms, we find an equation for the a coefficient, and we find an equation for the b coefficient. By using the definition of the gamma factor, it can be seen that these two equations are equivalent. So let's pick one of the two equations and solve for a. We can write the spinor transformation in matrix form. Since we want to construct a Lagrangian that is invariant under Lorentz transformation, let's guess an expression that might be Lorentz invariant. For example, the squared modulus of the spinor. However, if we transform this quantity according to the transformation rule that we found, we find that it is in fact not Lorentz invariant. So let's instead consider a slightly different quantity, where we introduce the gamma matrix of the time component. This yields a minus sign for the last two components of the spinor. If we see how this quantity transforms under Lorentz transformation, we find that it is indeed invariant, provided that a squared minus b squared equals 1. This motivates the introduction of a quantity called the Dirac adjoint. When we multiply a spinor with its Dirac adjoint, we obtain a Lorentz invariant scalar. Now that we have two independent equations for A and B, let's solve for them. From the second equation, it follows that A and B can be written as the hyperbolic cosine and sine of some unknown quantity x. So if we divide the two, we obtain the hyperbolic tangent of x, whose value follows from the first equation. We will now write the Lorentz transformation in terms of hyperbolic functions and see how we can relate them to the hyperbolic functions in the spinor transformation. We can write the Lorentz transformation in matrix form and calculate the difference of the squares of two matrix elements. By using the definition of gamma, we find that this expression equals 1. Therefore, the Lorentz transformation can also be written in terms of hyperbolic sines and cosines of a quantity that is called the rapidity. Its value can be calculated by noting that the hyperbolic tangent of the rapidity is given by the ratio of two matrix elements. We will now see how this rapidity is related to our new quantity x. We write the hyperbolic tangent as the hyperbolic sine divided by the hyperbolic cosine. We plug in the definitions of these functions and multiply the expression by 1. We write out the product and rewrite the result in terms of the hyperbolic sine and cosine of twice the rapidity. This can be expressed in terms of the hyperbolic tangent of twice the rapidity. We use this result to calculate the hyperbolic tangent of half the rapidity, and we plug in the values that we know from the Lorentz transformation. We can rewrite this expression to find that the hyperbolic tangent of half the rapidity equals the hyperbolic tangent of x. Therefore, we can conclude that x equals half the rapidity. And so we find how a Dirac spinor transforms under a Lorentz boost in the z direction, as is also reported in the early literature. We will now construct the Lagrangian for the Dirac equation, so that we can make it a field theory and apply Noether's theorem. The Lagrangian has to be Lorentz invariant, and we saw that to construct a Lorentz invariant quantity from the Dirac spinor, we have to use the Dirac adjoint. So we can construct a Lorentz invariant Lagrangian by using the Dirac adjoint, and we can verify that the Euler-Lagrange equations yield the Dirac equation. If we take the derivative with respect to the Dirac adjoint of psi, we find the Dirac equation for psi. And if we take the derivative with respect to psi, we find the complex conjugate of the Dirac equation for the Dirac adjoint of psi. Now that we have found the Dirac Lagrangian, we can apply Noether's theorem to find the expressions for the charge density and current density. If we know the Lagrangian, and it satisfies a certain symmetry, then we can immediately apply Noether's formulas. So we note that the Lagrangian is invariant under a global phase shift, and then we write down the expressions for the charge and the current. We plug in the Lagrangian for the Dirac field, and then we can rewrite the expression by using the definition of the Dirac adjoint and recalling how the gamma matrices relate to the alpha matrices. We find that the charge density is given by the squared modulus of the Dirac spinor, and the different components of the current density are calculated with the different alpha matrices. We will now find the plane wave solutions to the Dirac equation, so that we can later apply second quantization. We want to find solutions to the Dirac equation that can be written as some four-dimensional vector u times a complex exponential that depends on the momentum and energy. When we plug this solution into the Dirac equation, we can write down a matrix vector equation, where the time derivatives have turned into the energy, and the spatial derivatives have turned into components of the momentum vector. We can verify that a certain vector u solves this equation by plugging it into the matrix vector equation. For example, We can consider the top equation and plug in the energy-momentum relation. If we rewrite the energy-momentum relation, we find that the expression indeed reduces to zero. The same can be demonstrated for the other equations of the matrix vector equation. We can find 4 different vectors that solve the matrix vector equation. If we consider the first 2 vectors for the case where the momentum is equal to 0, we find that the energy is equal to mc squared. For the other 2 vectors, the energy is equal to negative mc squared. So we have 2 positive energy states and 2 negative energy states. For non-zero momenta, it means that we have to take the positive or negative square root solutions of the energy-momentum relation. We can rewrite the negative energy states in terms of the absolute value of the energy. We will now calculate the normalization constant so that the vectors have length 1. We can calculate the length of the first vector and rewrite the squared momentum by using the energy-momentum relation. We multiply the numerator and denominator with c and write the expression as a single fraction. One can verify that the same normalization constant applies to all 4 vectors. We have now found the plane wave solutions to the Dirac equation with a certain energy and certain momentum. There are 2 positive energy states that correspond to the 2 spins of the electron, and there are 2 negative energy states which are related to positrons. We now have the tools that are necessary to calculate the electromagnetic field that is generated by an electron according to the Dirac theory. We recall the expressions for the charge and current density that we found with Noether's theorem. We can write the wave function as a linear combination of plane waves. According to the theory of second quantization, we can turn the single electron wave function in a many-electron field by promoting the Fourier coefficients to annihilation operators. The product of a creation and annihilation operator yields the number operator, which counts the number of electrons in a certain mode. Since electrons are fermions, which obey the Pauli exclusion principle, the creation and annihilation operators satisfy an anti-commutation relation. We can now calculate the charge density of an electron in the Dirac theory. By plugging in the plane wave expansion, we find a double summation of creation and annihilation operators. According to the positron theory, or Hall theory, the vacuum state consists of an infinite sea of electrons that occupy all the negative energy states. The observable charge density, if a positive energy electron is present, is given by the difference between the charge density of that state and the charge density of the vacuum state. To find how the charge of a single electron is spread out over space, we use the correlation function to calculate the probability of finding charge that is separated by some distance xi, no matter the position r of the electron. For convenience of notation, we define the 2 coordinates r1 and r2. We can now plug the expression for the charge density into the correlation function. The products of the wave functions become double summations of the creation and annihilation operators. If we expand the product, we find a quadruple summation of creation and annihilation operators. We find 2 products of the vacuum charge density with the double summation of creation and annihilation operators, and we find the square of the vacuum charge density. To find the expected correlation function for a fixed number of electrons, we need to look at the diagonal elements in the Fock basis. That is, we should only look at the combinations of creation and annihilation operators that reduce to number operators. We find such terms in the quadruple summation when the first index is equal to the second index and the third index is equal to the fourth index. Alternatively, the first index can be equal to the fourth index, and the second index is equal to the third index. For the cross terms, the 2 indices should be equal to each other, and we consider the expectation value of the vacuum charge density. For the final term, we also take the expectation value of the vacuum charge density. We now use the number operator and the anti-commutation relation to rewrite the expression for the expected correlation function. With this result, we can compare the charge distribution of an electron according to two theories: the single electron theory, where we disregard the negative energy states, and the positron theory, where the negative energy states are occupied by the Dirac sea. If we consider the single electron theory, then we set the electron number for one state equal to 1, and the electron number for all other states are 0. The vacuum state is 0 as well. The electron wave functions are described by two-dimensional vectors, since we ignore the negative energy states. If we plug this into the expression for the expected correlation function, we find that in the first double summation only one term is non-zero. In the second double summation, the only non-zero terms are those where the first occupation number corresponds to the occupied electron state, and the second occupation number corresponds to all the unoccupied electron states. We can collect the resulting two terms into one single summation. If we plug in the expressions for the electron wave functions and substitute the definitions for R1 and R2, then we find that the integrand depends only on the position difference vector psi. The summation over all electron states can be turned into an integral over all electron momenta, and we assume that the occupied electron state has momentum 0. The resulting integral reduces to a delta function. Therefore, we conclude that in the single electron theory, where we ignore the existence of positrons, the electron can be described as a point particle, since the electric charge has no finite spread. We will now see what happens when we consider the positron theory. The difference is that all negative energy states are occupied, and the vacuum state that has to be subtracted is non-zero. We first calculate the expectation value of the vacuum state. To do this, we simply sum over all negative energy states which are occupied by the Dirac sea. To find the expected correlation function for the vacuum state, we plug the electron occupation numbers into the expression that we found previously. So in the two summations, only the terms corresponding to the negative energy states are non-zero. In the third summation, the terms are non-zero when the first occupation number corresponds to an occupied negative energy state, and the second occupation number corresponds to an unoccupied positive energy state. When we plug in the expression for the vacuum state, we find that three terms cancel each other out. The correlation function is non-zero for the vacuum state because of charge fluctuations in empty space, due to electron-positron pairs being randomly produced. To find the expected correlation function for the charge of a single electron, we have to take the difference with the vacuum correlation function. To find the difference between the two correlation functions, we consider the extra terms in the summation due to the electron state becoming occupied, and we subtract the terms that vanish due to the electron state being no longer unoccupied. Three summations gain extra terms due to the electron state becoming occupied. One summation loses terms due to the electron state no longer being unoccupied. One term can be used to complete the summation over all positive energy states. Another term can be expressed in terms of the vacuum state, which can then be cancelled. The two resulting integrals look similar, except the coordinates r1 and r2 are interchanged. However, when we consider the spatial dependence of the electron wave functions, we can see that we are free to interchange r1 and r2, because we can change the sign of the dummy variable p. Therefore, We can simplify the expression as the sum over all positive energy states minus the sum over all negative energy states. We can evaluate this expression by recalling the plane wave solutions to the Dirac equation. We assume that the electron is in a positive energy spin-up state of zero momentum. For a fixed momentum value p, we consider the integrand summed over all positive energy states minus the integrand summed over all negative energy states. We calculate the inner products of the states. Then we can rewrite the squared modulus of the momentum using the energy-momentum relation. We then simplify the expression to find the final result for the integrand for a certain momentum state. To find the expected correlation function for the charge distribution of a single electron, we integrate over all momentum states. Note that compared to the result of the single electron theory, the integrand is divided by the energy of the state, which is a function of momentum. So while in the single electron theory all charge is concentrated in a single point, in the positron theory the charge has some finite spread. This is an essential consequence of properly taking positron theory into account. Moreover, it motivates charge renormalization. Recall that the idea behind mass renormalization is that the electron has some intrinsic mass and an additional electromagnetic mass. Either one of them can be infinite, but they can partially cancel each other out to result in a finite observable mass. Similarly, the electron has some intrinsic electric charge, but it polarizes the vacuum so that the charge is screened by a cloud of virtual positrons. The infinite bare charge and the screening charge cancel each other out to result in a finite observable electron charge. From the charge distribution that we calculated, it follows that the spread of the charge is of the order of the Compton wavelength. We can ask two questions. First, why would the existence of positrons cause the electron charge to spread over the Compton wavelength? Second, does this spread of the electron charge resolve all the divergences that occur if we assume that the electron is a point particle? To answer the first question, we note that in the positron theory, electron-positron pairs can be produced if we have enough energy. Therefore, if we want to consider only a single electron, then there is an upper bound to the momentum it can have. But if there is an upper bound to the momentum, then by Heisenberg's uncertainty principle, there must be a minimum spread in the position of the electron. When we calculate this spread, we find that it is of the order of the Compton wavelength. To answer the second question, of whether this spread in charge resolves the divergences of a point particle electron, Weisskopf remarks the following. The divergences occur because for a point electron, there is no lower limit to the wavelengths with which the electron can interact. The spread of charge that we calculated in the positron theory does not change this. This is because the radiation interacts with the charge density function, not with the correlation function, which is where we found the spread of charge. Therefore, the spread of charge over the Compton wavelength does not impact how the electron interacts with short wavelengths. We can now calculate the part of the electron's self-energy due to the interaction between the charge distribution and the electric field that it generates. Since we have already found the correlation functions of the charge density, it is convenient to express the self-energy in terms of these correlation functions. We can write down the expression for the energy of a charge distribution in a certain potential. We can calculate the potential that the charge distribution produces. If we plug in the expression for the potential in the expression for the energy, we can change the integration variable and conclude that the self-energy can be calculated directly from the correlation function of the charge distribution. We will first calculate the self-energy in the single electron theory. When we plug in the expression we found for the correlation function, we obtain the Fourier transform of the Coulomb potential, which we have to integrate over all momentum vectors. Using spherical symmetry, we can integrate over the length of the momentum vector. We find that the resulting integral diverges linearly with the upper integration limit. We now calculate the self-energy in the positron theory. We again use the Fourier transform of the Coulomb potential, but now the momentum integral contains the energy in the denominator. Due to spherical symmetry, we can integrate over the length of the momentum vector, and we find that now the integrand reduces to 1 divided by the energy. In the limit of large momentum, the integrand reduces to 1 divided by momentum, so the integral diverges logarithmically with the upper integration limit. This is the key result. By taking positron theory into account, the linear divergence of the self-energy reduces to a logarithmic divergence, which diverges much more slowly. Now that we have calculated the self-energy due to the electric charge of the electron, we will next calculate the self-energy due to the currents that are generated by the electron spin. We recall the expression for the current density that we found by applying Noether's theorem to the Dirac equation. We can calculate the magnetic vector potential from the current density via the Biot-Savart law. We can use this to calculate the solenoidal part of the electric field. That is, it's only the part of the electric field that is generated by the time-varying magnetic fields due to currents, not by the static charge density. The magnetic field is found by taking the curl of the vector potential. As we did previously, we expand the electron wave function in plane waves, and apply second quantization by turning the Fourier coefficients into annihilation operators. By using the expression for the current density, we can write the vector potential in terms of a double summation over creation and annihilation operators and their corresponding plane waves. Depending on which component of the vector potential we consider, we use the corresponding Dirac matrix. To further evaluate this expression, we plug in the plane wave solutions. We collect the complex exponential that depend on energy, and we collect the complex exponentials that depend on momentum. We recognize the integral over space as the Fourier transform of a spherical wave. We first apply a change of integration variables, and then we plug in the Fourier transform of a spherical wave. We can rewrite the denominator by plugging in the energy-momentum relation. We plug this result in the expression for the x-component of the vector potential. We can find the energies of the magnetic and electric field by calculating these fields from the vector potential. When we take the spatial derivative to calculate the magnetic field, we multiply with the momentum. When we take the time derivative to calculate the electric field, we multiply with the energy. To calculate the expected value of the energy, we consider only the diagonal elements. Therefore, the quadruple summation that we would get from squaring the vector potential reduces to a double summation, where the creation and annihilation operators combine to yield number operators. The Dirac matrix that we use depends on the orientation of the component of the vector potential that we consider. So if we assume that we have only a single electron whose momentum is 0, we can write down the expression for the magnetic field energy, and similarly, we can write down the expression for the electric field energy. We find that in the expression for the electric field energy, the denominator can be cancelled out. This yields the expressions for the magnetic and electric field energy due to one component of the vector potential. However, since there are two independent polarization directions, we have to multiply the expressions by a factor 2. We will now evaluate the expressions for the single electron theory and the positron theory. In the single electron theory, the inner product of spinors does not depend on the momentum. Therefore, the integral over all momenta diverges with the third power of the upper integration limit. For the energy of the magnetic field, we observe that in the limit of large momenta, the denominator scales as p squared, so that again the integrand does not depend on the momentum. Therefore, we obtain for the magnetic field energy the same divergence as for the electric field energy. When we consider the positron theory, we have to recall the Dirac spinors for the positive energy states and the negative energy states. For simplicity, we consider a particular case where the Dirac matrix corresponds to the x component. The electron is in a positive energy state with spin up and zero momentum. We multiply this state with the Dirac matrix. For a fixed momentum, we calculate the difference of inner products for positive and negative energy states. We can rewrite the squared momentum with the energy-momentum relation. The resulting expression can be simplified to yield minus mc squared over E. We apply the same procedure for the magnetic field energy, but now there is an extra denominator that we need to take into account. Note that the denominator is different for the positive and negative energy states, because the denominator depends on the energy. We again rewrite the squared momentum with the energy-momentum relation and simplify the first term. We write the two terms as one fraction with a common denominator. The denominator of this expression can be simplified by using the energy-momentum relation. In the numerator, we expand the squares and find that many terms cancel when we expand the two products. We collect the terms and then divide the numerator and denominator by m to the third times c to the sixth. The numerator can be simplified with the energy-momentum relation, and the resulting fraction can be simplified. The formula for the magnetic field energy contains a factor of p squared, which cancels with the p squared in the denominator. So we find for the magnetic and electric field energy the same result, except for a minus sign. When we calculate the integral over all momentum vectors, we can use spherical symmetry to write it as an integral over the magnitude of the momentum. In the limit of large momenta, the integrand scales linearly with momentum, so the integral diverges quadratically. To find the next divergent term, we subtract this limiting behavior and find what remains. For large momenta, we can approximate the denominator by Taylor expanding the square root. We plug in this result and then Taylor expand the fraction. When we cancel two terms, we find that after subtracting the main diverging term, the integrand goes as 1 over p, so the integral diverges logarithmically. So when we calculate the energy integral, we find a quadratically divergent term and a logarithmically divergent term. We can rewrite it slightly by taking out a common factor. At this point, we must note a discrepancy with the result that Weisskopf presents in his paper. In Weisskopf's result, the quadratically divergent term is twice as large as the one that we find. This difference is significant because it affects the main conclusion of this calculation, where the quadratic divergences ultimately cancel out. I am not sure how to resolve this discrepancy while still arriving at the desired conclusion. It is worth noting that in an older calculation by Weisskopf, he did indeed make a mistake, which was noted by Wendell Furry, and Heisenberg repeated the calculation. So on the one hand, one might expect that Weisskopf's new calculation, which we are currently discussing, should by then be free from error. On the other hand, it is noted that before a properly covariant formulation of quantum electrodynamics was found, all calculations of the electron self-energy were plagued by errors and uncertainties like these. At any rate, let's for now complete Weisskopf's calculation to arrive at his conclusion, which played an important role in Bethe's calculation of the lamp shift. So we found that in the positron theory, the electric field energy has the opposite sign as the magnetic field energy, whereas in the single electron theory, they have the same sign. In the single electron theory, the energy diverges with the third power, but in the positron theory, we have a quadratic divergence and a logarithmic divergence. We can simplify the constant factor that is in front. Now that we have found the electron self-energy due to the charge distribution and due to the current distribution, we will next consider the final contribution to the electron self-energy, namely the interaction of the electron with the vacuum fluctuations. To study this interaction, we start with the Dirac equation. The interaction with an electromagnetic field is found by subtracting the vector potential from the momentum. We could then follow the method of perturbation theory, where we define an interaction Hamiltonian and see how this perturbs the wave function. We can then consider the expression for the current and see how the perturbed wave function leads to a current that is induced by the vacuum fluctuations. However, when Weisskopf performed this calculation, he obtained a result that can be interpreted in a much simpler way. From the change in electron momentum, we can infer a change in the electron velocity. Since the current is given by charge times velocity, we can immediately find the current that is induced by the electromagnetic field. This induced current interacts with the electromagnetic field that it was induced by, and this yields another contribution to the electron self-energy. We find that this energy is proportional to the mean-squared fluctuations of the vacuum field. To calculate this quantity, we consider the expression for the quantized vector potential. For the vacuum state, only the term with the creation operator yields a non-zero value. Moreover, we have to sum over the two polarization states. The integral over all spatial frequencies can be written as an integral over the magnitude of the spatial frequency because of spherical symmetry. The spatial frequency can be related to momentum, so we find that the self-energy due to vacuum fluctuations diverges quadratically with the upper integration limit. We have now calculated all the different contributions to the electron self-energy, and now we can put them together. To see how the contributions should be combined, we consider the Dirac Hamiltonian of an electron that interacts with an electromagnetic field that is described by a vector potential and a scalar potential. We can identify the interaction Hamiltonian and use perturbation theory to see how it perturbs the energy. We find that this expression can be written in terms of the charge density and the current density. The scalar potential is the one generated by the electron itself, and the vector potential consists of the one generated by the electron and the vacuum fluctuations. When we relate the sources to the potentials via Maxwell's equations, we can express the self-energy in terms of the electric and magnetic fields that are generated by the electron. The term due to the vacuum fluctuations can be written in terms of the current induced by those fluctuations, because only those currents are correlated to the vacuum fluctuations, so the time average of the product doesn't vanish. The electric field can be decomposed in an irrotational part that is due to the charge density and a solenoidal part that is due to the time-varying magnetic field generated by the currents. We can interpret this expression as the sum of three contributions: the self-energy due to the electrostatic field, the self-energy due to the electron spin, and the self-energy due to interaction with the vacuum fluctuations. We now use the results that we found to calculate the total self-energy in both the single electron theory and the positron theory. we found that the self-energy due to the electrostatic field diverges linearly in the single electron theory and diverges logarithmically in the positron theory. The self-energies due to the magnetic field and the solenoidal electric field diverge with the third power and have the same sign in the single electron theory. Therefore, they cancel each other out when calculating the self-energy due to the electron spin. In the positron theory, on the other hand, the two self-energies have opposite sign, so they don't cancel out. We have a quadratically divergent term and a logarithmically divergent term. This is the result where we found an extra factor of 1/2 in the quadratic term compared to Weisskopf's result. The self-energy due to vacuum fluctuations is the same for both theories, and it diverges quadratically. This expression is consistent with Weisskopf's result. We see that if we ignore our extra factor of 1/2 and thus accept Weisskopf's result, then the quadratically divergent terms cancel out when we add all the results together. Therefore, the self-energy would then only be logarithmically divergent. This is the key result of Weisskopf's paper. By properly taking the positron theory into account, the self-energy of the electron is only logarithmically divergent, instead of linearly or quadratically. We will see how this result plays an important role in Bethe's reasoning when he calculated the lamp shift. Freeman Dyson recalled how a conference in 1947 on Shelter Island would inspire Bethe to calculate the lamp shift. During this conference, it was discussed how the experimental result of Lamb and Rutherford can be explained theoretically. Hendrik Kramers proposed that if the infinite self-energies are removed via mass renormalization, one would find a finite interaction energy of the electron and the vacuum fluctuations, which would explain the Lamb shift. However, he did not know how to actually perform this calculation for a hydrogen electron. But Hans Bethe did, and so after the meeting, he performed the calculation on the train from New York to Schenectady. Even though the calculation was short, it was considered a turning point in physics. Before this calculation, there were those who thought that existing theories were fundamentally flawed, and revolutionary new concepts were needed. Julian Schwinger would later describe the attempts at finding those revolutionary new concepts as mutilations of the theory, which have been uniformly unsuccessful. Bethe's simple calculation demonstrated that the existing theory of quantum electrodynamics was fundamentally correct, but it just needed some new technical tricks. In his paper, Bethe notes that the energy shift observed by Lamb and Rutherford could not be explained with the existing theories, since they would predict infinite energy shifts. He notes that this is due to the electromagnetic mass, which diverges for a point electron. Therefore, the divergent electromagnetic mass for a free electron must be subtracted to get a physically meaningful result. In other words, one should renormalize the electron mass. Bethe finds that in his non-relativistic calculation, applying this procedure only reduces a linear divergence to a logarithmic divergence, but any physically sensible result must be convergent. This is where Bethe recalls Weisskopf's result, namely that positron theory without renormalization also reduces a quadratic or linear divergence to a logarithmic divergence. Therefore, Bethe expects that if one combines renormalization with positron theory, one gets a double reduction in the divergence, and the result should be convergent. However, he did not actually perform the fully relativistic calculation. In this paper, Bethe performs a non-relativistic calculation and makes some approximations and assumptions to obtain a finite answer from a logarithmically divergent expression. It is by no means a rigorous calculation, but it was convincing enough to motivate others to develop a fully relativistic, renormalized theory of quantum electrodynamics to calculate physically observable quantities, such as the lamp shift. So let's recall the interaction Hamiltonian in the non-relativistic theory. The states we consider in the second-order perturbation theory are the orbitals of the hydrogen atom. These orbitals are very localized in space, as opposed to the plane waves that we considered previously. Therefore, we can assume that the linear phase in the vector potential is evaluated at only a single point. This is called the dipole approximation. Moreover, we can apply a non-relativistic approximation to the energy levels of the atomic orbitals. For example, if we consider the energy of the intermediate state, then we can write the electron energy as the sum of its potential energy and kinetic energy. In the non-relativistic approximation, we assume that the kinetic energy is small, so it can be neglected. That is, the energy of the electron is assumed to be only due to the electrostatic potential generated by the atomic nucleus. Finally, we apply mass renormalization. To find the experimentally observable perturbation to the energy, we must subtract the energy perturbation for a free electron that is not affected by the electrostatic potential of the atomic nucleus. This eliminates the infinite electromagnetic mass from the calculation. With these approximations, we can calculate the second-order perturbation to the electron energy due to interaction with the vacuum fluctuations. We write down the expression for the bound electron, and we subtract the expression for the free electron. We can write the difference as a single fraction. We will now calculate the squared matrix element, summed over the two polarization states. If we have a certain momentum vector, then we can project it onto the two polarization directions, which are orthogonal to the photon momentum vector. Using the Pythagorean theorem, we can write this in terms of the projection along the photon momentum. This projection can be calculated using the cosine of the angle between the electron momentum vector and the photon momentum vector. So if we recall the expression for the renormalized energy perturbation, we can plug in the expression for the squared matrix element. We can further rewrite the expression by collecting all the terms that depend on the photon momentum vector and write the integral in spherical coordinates. The integral over the angular coordinates can be calculated to be 8 pi over 3. The integral over the magnitude of the photon momentum yields a logarithm of the upper integration limit. So we find that the energy correction is logarithmically divergent, whereas in the non-relativistic correction without mass renormalization, the correction was linearly divergent. We assume that all the electron energy differences are negligible compared to the maximum photon energy. Since the gradient of the logarithm is small for large arguments, it is assumed that we can substitute the electron energy difference in the denominator with a fixed average value, so we can pull the logarithm outside of the summation. We now need to calculate the sum over all electron energy levels. To calculate the sum, we first rewrite the squared modulus of the momentum matrix element. One energy is constant, so we can take it outside the sum. The other energy, that we sum over, we put before the momentum operator. We now use the fact that these energies are eigenvalues of the Hamiltonian. We identify the identity operator in the sum, so the summation can be eliminated. We recognize in the two resulting terms the commutator of the momentum operator and the Hamiltonian. The momentum operator expressed in the position basis is given by the gradient operator. The commutator of the momentum and the Hamiltonian is equal to the commutator of the momentum with the potential energy, because the momentum operator commutes with itself. If we calculate the commutator, then we find by using the product rule that it is equal to taking the gradient of the potential. Therefore, we can write the expression as an integral of the gradients of the potential and the electron orbital. Using integration by parts, we can write it in terms of the Laplacian of the potential. We can further evaluate the expression by plugging in the Coulomb potential of the hydrogen atom. Its Laplacian is equal to the delta function, so the integral reduces to the squared modulus of the orbital evaluated at the center of the atom. We plug this result in the expression for the perturbation to the energy. We see that this energy perturbation is zero for orbitals whose orbital angular momentum is non-zero. In case the orbital angular momentum is zero, we can plug in the value for the orbital at the center of the atom. We can write the energy perturbation in terms of the Rydberg energy, which is the energy that is required to ionize a hydrogen atom in the ground state. It can be written either using Planck's constant or the reduced Planck's constant. After we write the energy perturbation in terms of the Rydberg energy, we can plug in the expression for the Bohr radius. This yields the final expression for the energy perturbation due to interaction with the vacuum fluctuations. This is the formula that Bethe arrived at, and when he evaluated it numerically, he found an energy shift that was very close to the experimentally observed value. Note that Bethe assumed that the maximum photon energy is equal to mc squared, which is arguably a somewhat hand-wavy step in the calculation. Nonetheless, this result demonstrated that interactions with vacuum fluctuations are real, since they yield an observable energy shift. To calculate this energy shift, we had to subtract the infinite electromagnetic mass of a point electron in a procedure that is now known as mass renormalization. Bethe's calculation used a non-relativistic approximation, which resulted in a logarithmic divergence that was cut off with a hand-wavy assumption. But a fully relativistic treatment is expected to get rid of the logarithmic divergence and yield a finite result. We thus see why the lamp shift experiment is considered a landmark in physics, since it provided direct experimental evidence for quantum field theory.